Introduction. There were 4 questions provided for the group project in CSC510 course. And each group was required to select one question. After the discussion among the group members, our team decided to choose question 2, which focuses on the properties of relation, specifically reflexive, symmetric, and persistent relation. Problem statement. First, problem. Students often make mistakes when manually determining multiple relation properties and their closure. 2. Functionality. The program allows users to enter element and relation pair, check whether the relation is reflexive, symmetric, and transitive. Also, calculate and display the corresponding closure. 3. Need. A computerized system is needed to automatically analyze relation properties and their closure. For benefit, the system minimize error, improve accuracy, save time, and help user to understand more about relation properties. Flowchart. The program check 3 properties of a relation. First, reflexive, second, symmetric, and third, transitive, and build a closure for each one. We start by asking for the number of elements and validate the input. Then it look to collect each pair in the relation, which is element A and element B. Once all pairs are in, we check reflexive or not, whether A exists for every element in the set. It brings the result, then generate the reflexive closure, regardless of whether the relation was already reflexive. Next, come to check symmetry or not. Whether A, B exists, means B, A also exists. Same pattern, print the result, and build the symmetric closure. For third one is check transitive or not. Whether AB and BC together, mean AC exists. B is the shared middle element that connecting the two pair. And transitivity require that shortcut to exist. It prints the result and build the transitive closure. At the end, the program displays all the pair along with their closure. One last check, run across all 3 properties. If the relation for one of them, it print which one. If not, it print none.
Okay, now I will talk about our programming code. First, we will find reflexive properties. We define function reflexive that take in our set of element A and the relation R. Inside, we use range-based for loop to iterate through the every element A in set of A. For each element, we search the relation R for the pair using the find method. If R.find reach the end of the relation without finding the pair, it means a required reflexive link is missing, so we immediately return it as false. If the loop finishes checking every single element without any issue, it means every element has its corresponding pair. So we will safely return true because the relation is successfully verified as reflexive. Now I will talk about the symmetric properties. Looking at the code, we have this symmetric function and we just running a for loop to look at every single pair inside the relation. Inside the loop, we split the pair into its coordinate A and B. Then we use r.find to search for the reverse pair B and A. If it hits r.n, that means the reverse pair doesn't exist. At the moment we find even one missing partner, the function instantly returns false and stop. But if the loop finish and everyone has a match, we go to return the true. Okay, now I will talk about transitive. So we will looking for change in the data and we will use a nested loop which is use two loops. The first loop will grab a pair A, B, and the second loop will look for a connecting pair that start with B, which give us our C. Once we find a chain from A to B to C, we will check if the shortcut AC exists in the relation. If it's missing, the whole thing fails right there and we return as false. If the loop finish without any issue, we just return hash chain and we will make sure we actually found at least one connection instead of empty. So now how to find reflexive closure? First, we will create a copy of our original relation that called result, so we don't mess up the original data. Then we will just use the loop to go through every single element in A in our set of A. Inside the loop, we will call result.insert to add the self-matching pair. Because relation is a set, we don't even need to check if the pair is already there or the data structure automatic ignore any duplicate for us. Once the loop finish adding all those missing self pair, we just return the update result. Okay, now let's talk about symmetric closure. First, we start by making a copy of our original relation and store it in result. So then we use a loop to go through every single pair inside the relation. Inside the loop, we will call result.insert and we'll flip the element by putting p.second first and p.first second. This will take every AV pair and attempt to insert it by reverse. Now we have relation, meaning that duplicate are automatic handled. If the reverse pair is already in relation, the insert function just safely ignore it. Once the loop finish, process every pair, we will return the update result.
Implementation of Warsaw algorithm to find the transitive closure of a relation. We start by taking our set of elements A and copying them into a flat vector called elements. This gives us a fixed order so we can map abstract data into numerical index using our helper lambda function IDX. Next, we create an n times n Boolean matrix initialized to false and loop through our initial relation arc, flipping the corresponding cells to true to present all direct connections. Before running the full algorithm, we perform a quick optimization check. We use a Boolean flag hash chain and scan the matrix using nested loops. If we find a direct connection from I to J, we instantly look to see if J connects to a third node, K. If such a chain exists, we set a hash chain equal to true and break early. This lets us know if there is any pre-existing transitivity in our datasets. If no chain exists at all, we execute a fallback mechanism designed to bridge isolated components together. Using a 4-level deep nested loop, we look for any active relation I to J and search for a completely separated relation K to L. When we find one, we deliberately bridge the gap by setting map JK equal to true, creating a synthesized change running from I all the way to L. Finally, we run the classical Warsaw algorithm triple nested loop. Crucially, the intermediate node K is on the outside. The logic evaluates if path I to K exists and path K to J exists, then a direct transitive path I to J must also exist. Once the matrix is completely updated, we loop through it one last time, convert the true cells back into our original element pairs, and return the finalized result relation.
Next, this is the interface of our system. To check our program accuracy on determining properties of relation and closure for each properties, I already set an example. First, I enter A as number of elements which are 1, 1, 2, 2, 3, 3, 4, 4. 1, 2, 2, 1, 3, 4, 4, 3. Then the program will automatically detect our set of relation is reflexive, symmetric and transitive or not. For this example, the set of relation is reflexive because 1, 1, 2, 2 is element of R. The relation is also symmetric because 1, 2 and 2, 1 is element of R. Besides that, the relation is transitive because 1, 2 is element of R, 2, 1 is element of R, and 1, 1 also element of R. So, the final result shown by the system is that this relation is reflexive, symmetric, and transitive. In conclusion, we successfully developed a C++ program that can check whether a relation is reflexive, symmetric, and transitive, and generate the corresponding closures. This project helped us apply the concept learned in discrete structure in a real programming environment and improve our understanding of relation properties and closure operation. It also strengthened our problem solving and C++ programming skills. Besides that, this project taught us the importance of teamwork, communication, and time management. By working together, we were able to solve problems during development and ensure that the program met the requirements. Overall, this project provided valuable experience and built a strong foundation for our future studies and careers in computing.